Hello everyone, my name is Ali Berkakçay and I'm a first year electrical and electronics engineering student at Bilkent University. Today I'm going to present you my digital logic design courses term project. My project is called dual channel arbitrary waveform generator. So the way my project works is that we calculate 256 points in the waveform that we want, and then we send those points digitally from base history into the digital to analog converter circuits here. Then the output signal goes into a low pass filter where it's cleared from noise. Then we have a non-inverting amplifier circuit with potentiometer so that we can control the voltage. Then that gives us our output signal, but we also put it through a voltage divider and then into the JX-ADC port of base history so that we can see the voltage while we are adjusting it through the 7-segment display. So it has two modes for each channel. We have the standard mode and the arbitrary mode. The first three switches control channel 1 and the second three switches control channel 2. Right now we have sawtooth for both of the channels, and both of the channels are in standard mode. We can have sawtooth wave. Let me adjust it a little bit. The triangle wave, the square wave, and the sine wave from the standard mode. We can adjust the voltage here. As you can see on the oscilloscope, the amplitude grows, and we can also observe it from the 7-segment display as well. As I'm adjusting it, it's increasing. And we have this Python software here, and here we can control the arbitrary function and also the frequency. Right now we have 1 kHz for both of the signals, and I can change it from here to 2000 Hz. And as you can see on the oscilloscope, our frequency doubled. And also the switch, the rightmost switch controls which voltage we are seeing, which channel's voltage we are seeing. So as you can see right now I'm at channel 2 and I'm adjusting it. Then I can go to channel 1 back by turning off the switch. In the software we have, we can get all the USB ports connected through this part. We can refresh, we can disconnect, we can connect back. Right now I only have one USB connected, so it is only seeing that. And we have the arbitrary functions part. Here we can enter any function we want. I am going to enter sin x over x and cosine x squared. These functions we don't have as standard waveforms. I'm entering 0.001 so that it's never 0 divided by 0, and I'm going to enter 4 pi here, which is which should be around this, and I'm going to enter 4 pi here as well. It should be 0. Let's enter equal frequencies. And we also have the preview waveforms functionality here. Before we send our data to the base history FPGA board, we can see how the waveforms are going to look like. Now let's send them to the FPGA. And in order to enable arbitrary mode, we have to turn on the third switches. And as you can see, we have the correct waveforms. The Python software also allows us to calculate the integral of the functions and have them as the output. As you know, normally sin x over x is a non-integrable function. However, we use numeric integration, so we can take the integral of that. And for the second function, I'm going to have e to the minus x squared. Let's have the same frequencies. Another parentheses here. And as you can see, we have those signals and we can check them from here, and they seem correct. We can also use this functionality to draw pictures. Now I'm going to use the Lissajous patterns to draw a flower. I'm going to adjust the interval to 2 pi. We will have cosine 5x times cosine x, and then on the y-axis we will have cosine 5x times sine x from 0 to 2 pi. We have tried some frequencies for the flower shape, and the one that works best is 430 Hz, and as you can see we have a flower shape with 5 leaves. And now I'm going to write the equations for the heart shape. 16 times sine cubed, and here we will have 13 times cosine x minus 5 times cosine 2x minus 2 times cosine 3x and then minus cosine 4x. And as you can see we have the heart shape, and we can also draw shapes that can move around. For example, normally sine x graphed against cosine x would give a normal circle, but we can make their frequencies a little bit different, and that will result in a ring that is rotating like that. So that was my EEE102 course project. Thank you for listening to me.